Welcome back to another video. Today we are going to show that the greatest common divisor of a raised to the 2 to the m plus 1 and a raised to the 2 to the n plus 1 equal to 1 if a is an even integer, equal to 2 if a is an odd integer. If a when a and n are positive integer and m must be greater than n. Okay, let's prove this. So the first thing I'm going to do is to let a, m, and n be positive integer. Okay, and then these two terms are, I think I'm not gonna write. If I write so many times, it's going to be a waste of time. So I'm going to define, let's define a sub k to be a raised to the 2k plus 1. I just want to make it simple. Okay, write this simple term that denote a to the 2 to the a to the 2 and raised to the k plus 1 for, what is k? For k, for any positive integer k, including, let's include 0. Okay, great. Now, once we define this one, so what do I want to do? I want to write a to the n plus a to the 2m plus 1 in the product of something that contain this term. So we want to start with this. Let's start with a to the 2 to the 1 minus 1, which is a to the 2 equal to minus a to the 2 minus 1, and it can be factorized into a minus 1 times a plus 1, which is a minus 1 times a to the 2 to the 0 plus 1. Okay, let's try to do again. Let's have the case where a raised to the 2 raised to the power of 2, we're gonna have a to the 4 minus 1, which is a square minus a square plus 1. So a square plus 1 cannot be factorized, but this term right here is this one, right? So we gonna have a minus 1 as the first term, and a squared to the 0 plus 1 times a to the 2 plus 1. And a to the 2 is a raised to the 2 raised to the 1. Next one, a to the 3, a raised to the 2 to the 3, which is a to the 8 minus 1, which is a to the 4 minus 1, a to the 4 plus 1, which is, okay, what is a to the 4 minus 1 is up here. So we gotta have, okay, so we gotta have a minus 1, a to the 2 to the 0 plus 1, a to the 2 to the 1 plus 1, and the last term right here is a to the 4. A to the 4 is a to the 2 to the 2 plus 1. Okay, it seems that we're gonna have this formula. We're gonna have a to the 2 to the k, okay, minus 1 equal to a minus 1 times which term? The product of this term. Let me write this product, which is the big pi, that is that denote the product of consecutive terms. Okay, so we start from I equal to 0 to k minus 1, because this is 3 and the last term is n with 2. So we're gonna have a to the 2 to the I plus 1. Okay, and this term right here is ai. So we gonna have a minus 1, the product of ai, start from I equal to 0 to the k minus 1. Okay, great. And then what do we have? once we have this formula. So this formula can be shown by using the mathematical induction, okay? And I want to rewrite this term in terms of a sub k, but this is a raised to the 2k minus 1. So this term is just a to the k minus 2, right? Because when you minus 2, you're going to have 1 minus 2, which is minus 1. So it turns out to be a sub k minus 2 equal to a minus 1. The product from I equal to 0 to k minus 1 of ai. Okay? Okay, great. So let's go to these two terms. So these two terms right now can be written as, so this is am and this is an. Okay? But we know that m is greater than n. So what do we have right here? So let's take a look. So when we have m, which is positive integer, which is greater than n, what do we have? We gonna have m equal to n plus r, right? Where r is a positive integer. So where r is an integer and greater than 0. Now, what happened to this term am, which is a to the 2 to the m plus 1. So I want to start with this term right here. I will substitute m into here. Once you substitute m, what do we have? So we gotta have am minus 2, okay, equal to a1, the product of I equal to 0 to k minus m, okay? To the m minus 1, a sub I. And do not forget that a sub k is a to the 2 to the k plus 1, okay? So am minus 2 is going to be a to the m equal to a to the 2 to the m minus 1. So let's write this down. And what is this m? This m right here is a minus 1, and the product from I equal to 0 to m, our m is n plus r, okay, and minus 1 and ai, okay? So we gonna have a minus 1 times a0, a1, a2, and dot 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 all the way to an plus 1, and all the way to an plus r minus 2, an plus r minus 1. Okay, great. Then what next? We have this an, okay? So we can have an times the product. We have this an right here. I just want to write an in the front of all the rest of the term. So we gotta have a1, okay, a0, a1, a2, all the way to an minus 1. Now an is here, so the next term must be an plus 1, and all the way to an plus r minus 2 and an plus r minus 1. Okay, great. So what do we have here? We have an as the divisor of am minus 2, right? Okay, so since this term is an integer, okay, this is an integer, and we have am minus 2 equal to this term. Okay, let me write it down here, equal to this term. So what do we have? So we gonna have that, what do we have? an, right? This is an and this is an integer. So an divide am minus 2, right? Am minus 2, just like that. Okay, and then we have shown that if m is greater than n, then we have this divisibility. A sub n divides am minus 2. Okay, great. Then what next? Okay, let me highlight this one right here. Then let's take a look at this greatest common divisor, which is a to the 2 to the n plus 1 and a to the 2 to the n plus 1. So I want to let d to be the greatest common divisor of a to the 2 to the m plus 1 and a to the 2 to the n plus 1. Okay, which is now am and an. So since d is this greatest common divisor, that means that d divide am and d divide an. Okay, and then what do we have next? We have this one. We have an divide. We have an divide am minus 2. Okay, and we have d, which is the greatest common divisor, divide an. Okay, so what do we have? Since an divide a minus 2 and d divide an, that means that d divide am minus 2. Okay, then what do we have next? Since d divide am, so what do we have? Since d divide am and d divide am minus 2. Okay, let me write this. So dex is integer q1 and q2 such that am equal to dq1 and am minus 2 equal to dq2. Okay, then what do we have? We can have q1d equal to what? Give me a second. q1d okay, so just plus 2, right? So we just add to both sides, so we can have just am. This am is now dq1. So we gotta have we gotta have q1d equal to q2d plus 2. Okay, then what do we have next? So let's move this one to the left side. We gotta have q1d minus q2d equal 2. So we gotta have d q1 q2 equal 2. And q1 and q2 is an integer. So since q1 minus q2 is an integer and dq1 minus q2 equal to 2, what does it mean by this? So we can write 2 in the product of d and another integer. That means that d divide 2, which is the greatest common divisor of these two terms. Okay, what next? So we will split into two cases. The first case is A is odd. The second case is A is even. Okay. So when A is even, what do we have? When A is even. Okay. So we're gonna have A to the 2 to the m and A to the 2 to the n are both even. Okay. So A to the 2 to the m plus 1 and A to the 2 to the n plus 1 are both odd. Okay, they are both odd, right? And since we have d divide a sub m, okay, this one right here, d sub m, and d is in d divide 2, and am is, I forget what am is. Am is, what is it actually? Okay, is a to the 2 to the m plus 1, right? Am is odd, but d divide 2. Okay, d divide an odd number and d divide 2. So and I can tell you this. Am is odd. Okay, so that means that d equal 1, right? When d divide 2 and d divide an odd number, the only case that possible is d equal 1. So therefore, the greatest common divisor of a to the 2 to the m plus 1, a to the 2 to the n plus 1 is 1. Okay, when a is even. Okay. Okay, the second case, let's take a look at the second case. When a is odd, what do we have when a is odd? So a to the 2 to the m and a to the 2 to the n are odd. Okay, they're both odd. So what do we have? So we're gonna have a to the 2 to the m plus 1 and a to the 2 to the n plus 1, they are both even. Okay, so they are both even, and since we have d divide a to the m and d divide a to the n, right? Okay, and d divide 2 and d divide 2, and we have the greatest common divisor of a to the 2 to the m plus 1, a to the 2 to the m plus 1, which is d. So d both divide this number, but d divide 2. So d must be the greatest common divisor of these two numbers, right? Okay, so d must be 2, because the largest divisor that divides 2 is just 2. Okay, so the greatest common divisor must be 2. Okay, so in this case, the greatest common divisor of 2 to the m plus 1, a to the 2 to the n plus 1 is 2 when a is odd. Okay, so therefore, the greatest common divisor of 2 to the m plus 1, a to the 2 to the m plus 1, okay, equal to 1, and equal to 1 and 2, right? 1 or 2. It is 1 when a is even. Okay, the greatest common divisor is 2 when a is odd. Okay, and this is the proof of this problem. So we have shown that the greatest common divisor of a to the 2 to the n plus 1 and a to the 2 to the n plus 1 is 1 when a is even and equal to 2 when a is odd. That's it for this video.